Welcome back to part two of the lecture. In the first part, we discussed two examples where we looked at two probability models for the movement of an oil spill. In this part, we are going to start with a new topic. Actually, it's called convolution. I have put it as an example here because there is something that we have to prove here. Convolution is used to find the probability distribution of the sum of two random variables. Suppose that x and y are two variables, two random variables with the joint density function f x y and define z to be x plus y. The main interest here is the density function of z. I think I'd like to make a small correction here because usually I write down the joint density of the two random variables x and y by f subscript capital X comma capital Y and then within bracket simple x simple y. But I have forgotten to do that here. Okay, so let's derive the density function of z, some expression actually, a general expression, because here I have not mentioned specifically the joint density, just assuming that the joint density is f. What I want is to get an expression for the density function of z in terms of the marginal densities of x and z, right? So, in order to get the density function of Z, we will use the method called the CDF technique. That is to first derive the cumulative distribution function, and then by differentiating that, we get the density function. So let us start with the definition. For some real number simple Z, let us look at f capital Z evaluated at simple Z, where this f capital Z denotes the cumulative distribution function of random variable Z, right? So that is by definition the probability that Z less than or equal to simple Z, but we know that Z is equal to x plus y, therefore we can write it like this. So in general, how do we get this probability? We have to integrate the joint density with respect to x and y over the region, sub-region in the support of the support satisfying this condition. That means we have to integrate over the set of all xy points satisfying x plus y less than or equal to z. Right. So satisfying this condition here. That's what we want to do. Okay, so now let us consider a fixed value of x. In that case, the variable y must satisfy y less than or equal to z minus x, because x plus y is equal to z. Y should be less than or equal to x for a fixed value of x. Because in order to integrate first, we have to uh, fix, we can do it two ways. What I usually do is fix fix at a given x value and then look at the stripe uh, and then find out the probability over that stripe and then move x to cover the whole set A, right? So therefore, when I am integrating with respect to y, keeping x fixed, then the limit of y will be from minus infinity to z minus x, right? Y less than or equal to z minus x. So I have to integrate the joint density with respect to y to get the volume under the stripe with uh, along the y-axis. And then we have to cover the whole area A. In order to cover the whole area A, we have to integrate with respect to x from minus infinity to plus infinity in general. Right. Of course, in a particular problem, we'll have to write down more accurately this limit here. But here in general, assuming that x can vary from minus infinity to plus infinity, you have to integrate over all possible x values. So this is the general expression that you can get in terms of the joint density uh, cumulative distribution function. Right. Now, in order to obtain the density function of Z, we have to differentiate this thing with respect to Z. Right? In order to get the density function of Z, we have to differentiate the cumulative distribution function f(z)z with respect to Z. So that is equal to the derivative of this function, and that function is this, right? Therefore, the derivative of that. But notice here, when we are integrating with respect to y and putting the limits, these limits, this part will be a function of z, z and x both. But because we are integrating with respect to z, we can take sorry, we are taking the derivative with respect to z. We can take the derivative inside here. So first take the derivative with respect to z, and then integrate the term coming out of that with respect to x, right? This is the same as this. But then using if you apply the fundamental theorem of calculus, you will see that here we are integrating with respect to y, limit from minus infinity to z minus x, and then the answer will contain x and z only, but we are taking the derivative with respect to z. So then what we get is this function by the fundamental theorem of calculus. That will be this function evaluated at this value for y. We have to substitute for y, but x will be keeping fixed. Right. So this part becomes this from the fundamental theorem of calculus. And so this is the expression that you can get as one expression for the density function of Z general. Right. But in a special case, if x and y are independent, then we can factorize this thing or write down this joint density as a product of two marginals. That is, this part will be equal to f of x evaluated at simple x times f of y evaluated at z minus x. Right. So that will be a special case of that. And it will come like this. If x and y are independent, then their joint density factors as of it can be factored as this, right? So similarly, therefore, this term can be factored as the marginal density of x at simple x and marginal density of y at z minus x. So then we have this particular expression. So this is what I mentioned at the beginning. We were trying to get an expression for the density function of Z in terms of the marginal densities of x and y. But that can be done only if x and y are independent. Otherwise, we have this general expression, right? But in this case, we have only one integration, but integrating with respect to x, the joint density. Right? So this integral is called the convolution of the two densities fx and fy in general. It describes how the two distributions combine to produce the distribution of the sum. Right. So that is the general equation. But then the special case when x and y are independent. Right. Now we will look at a particular application, right? Rather than just leaving with the theory, I'd like to look at some application, one or two applications. Right. So we will look at one well-known theorem actually. We already know that if x and y are both normally distributed and independent random variables, we already know that x plus y also has a normal distribution, right? That is a well-known result. But now I am going to get the same result using this convolution formula. Suppose x and y are independent, right? So we are going to look at get the distribution of x plus y using this convolution formula. We can apply this one because x and y are independent. Right. So let's take z to be x plus y. The question is, what is the distribution of z? Since x and y are independent, the density of z is obtained by the convolution formula, second convolution for this one. Right. So for that, we need the density function of x evaluated at x and density function of y evaluated at z minus x. So with this information here, x has a normal distribution with mean mu x and variance sigma square x. Y has a normal distribution with mean mu and variance sigma square y. Therefore, we know that their densities. Therefore, we can get fx. X is given by this expression. Fy z minus x is given by this expression. Right, instead of y, we have to substitute z minus x in the density function of y. So it's easy to get these two expressions, and then we have to substitute here and do the integration with respect to x to get the density function of z. So when I do that, the expression will be like this. If z is equal to, so this is integration, and some of the constants coming from here and here can be taken out. And then integration of this expression here. That is the same as what you get if you substitute these two into this expression. Now with a small substitution, say tau square is equal to this sigma square x plus sigma square y, we can write down this thing as a complete square, right? Like this, sum of two squares, this part, I'm considering only this part as this expression here plus a constant. So this is just mathematics, right? Usual completing square terms, right? So once you have that, then we can substitute here, and then you can see that we are integrating with respect to x. So the terms that doesn't contain x, like this term inside exponential, so you can take that also out, and then our expression will be like this. Now this is actually we can see that this has the form of a density function of a certain normal distribution, right? With some sigmas and some mu. For example, here you have x minus some quantity. It's like x minus mu divided by some other quantity. So you can say this is divided by this quantity divided by sigma square, right? 1 over 2 is also their negative sign. Yeah, so this part is like a x e to the power x minus mu over minus half x minus mu over sigma square part in a normal density function. So when you integrate that, we know that we should get 1 over root 2 pi sigma as the answer. That is the normalizing constant. So according to that, here sigma is going to be 1 over, sigma square is going to be 1 over this quantity. So therefore, you have to divide by that quantity. And then with this one, it simplifies to this quantity. Right? So you can simply look at this. This is direct substitutions. There's nothing much except some sort of mathematical simplifications. So therefore, you will be able to easily get this expression as the density function of z. And you can recognize this is the density function of a normal distribution with mean mu x plus mean mu y divided by uh, variance equal to tau square, where is equal to tau square, where tau square is equal to sigma square x plus sigma square y. So therefore, it gives us the well-known result already. But here we obtain it using the convolution formula. Right. Now let us look at another example. Here we are going to look at the sum of two independent uniformly distributed random variables on 0, 1. So that means sum of two independent standard uniform random variables. So find the CDF and PDF of the sum of two independent uniformly distributed random variables on 0, 1. Check the theoretical CDF via simulations also. So first we will get the CDF and PDF theoretically, and then we will do simulations and see whether the PDF looks like the theoretical one. Right. Okay. Suppose X has a uniform distribution in 0, 1 interval and Y also has a uniform distribution in 0, 1 and X and Y are independent. Right. Let us say Z is equal to X plus Y. Then X is between 0 and 1, Y is between 0 and 1. Therefore, we can easily understand that Z is between 0 and 2. Right? So let us select any simple Z value in this interval, 0, 2 interval. Then at that simple Z, the cumulative distribution function of capital Z, denoted by FZ, is by definition, that is the probability that Z less than or equal to simple Z, which is the probability that X plus Y less than or equal to simple Z. So in order to get this probability, naturally, we have to integrate the joint density function of X and Y with respect to X and Y over all possible X and Y satisfying this condition, right? Satisfying this condition, right? So again, as we did in the previous example, usually I keep X value fixed and then consider a stripe, vertical stripe, and then integrate the joint density over that stripe. And then take that answer and then integrate that part with respect to X, right? Where X will be changing in the relevant interval. Right? So in order to understand what that area should be, right, we should be integrating over certain area here. So we will look at the support of the joint density, right? The joint density here will be actually equal to the product of individual densities because X and Y are independent, right? So therefore, if X is going to be actually 1 in the interval 0, 1, if Y also going to be 1 in the interval 0, 1. So therefore, the product is also going to be 1, 1 times 1. But now the joint density, when you talk about joint density, we have to look at XY points. So XY points should be in the square 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1 square. That will be the area that we have to consider. But of course, we are looking at uh, that is the area for the joint density, right? But what we want is to find out this probability X plus Y less than or equal to Z. So that will be a subset of that support. That subset is shown here, right? Uh, Using two pictures because the picture will be different depending on the Z value, simple Z value that we select. This Z can be anything between 0 and 2, right? Z can be anything between 0 and 1. So as I mentioned, the support of the joint density is going x value is going from 0 to 1, y value is going from 0 to 1. But now what you want is the area that x plus y less than or equal to z. So that z, if that z is less than or equal to 1, right, then the area given by x plus y less than or equal to z will be like this, something like this, until it comes up to here, right? Until z becomes 1, right? Z becomes 1, then this line will come here, right? But then if we said greater than 1 but less than 2, then the x plus y is equal to z line will be something like this. Then therefore that area that we are looking at in that case will be this whole area, right? So therefore we can see that we have to get this expression, right? For two possible cases of z. One possible case of z is less than or equal to 1. The other case is z greater than 1 but less than or equal to 2, because z has to be between 0 and 2. Right. So let's look at those two cases. So first, let's consider this situation. In that case, I have to integrate, in order to get this probability here, I have to integrate the joint density over this area. So I can do that by, again, as I usually do, keeping um, x at a fixed value. So let me draw it here. Yes. This. So we can look at a vertical stripe like this with dx. Right. So we'll first integrate uh, the joint density over this small stripe, thin stripe. Then in that case, integrating with respect to y is changing from 0 here. This value will be then, because this is x plus y is equal to z. So y is equal to, in this case, uh, z minus x. Right. So you have to first integrate with respect to y from 0 to z minus x. And then x will be going from this value to this value. What is this value? This value will be, in this case, y is equal to 0. Therefore, x is equal to z. So therefore, you have to integrate first with respect to y from 0 to z minus x. And then the answer will have to be integrated from 0 to z to get uh, the area, actually volume, not the area, volume under the uh, joint density, which is equal to 1, uh, over this rectangle, not the rectangle, triangle here. And when z greater than 1 but less than or equal to 2, the probability z, that is x plus y, less than or equal to simple z, will be given by the volume spanned over this area. Right. So that is the same as 1 minus the volume spanned over this area, right? So the area spanned over this area is easy to obtain. So therefore, I will get the area spanned over this, not the area actually, volume. Volume spanned over this area is equal to 1 minus the volume spanned over this area. Of course, in this case, we don't have to do the integration also, because we know that the joint density, the value of the joint density is equal to 1, right? So therefore, the area will be just equal to, the volume will be equal to this area times just 1. And here again, the volume will be equal to, that is the probability. Volume spanned over this area will be area, this area times 1. Right. But anyway, let me first clean this. Right. So I have done the integration as usual, right? FZ Z is equal to this thing. And then as I mentioned, this is the joint density is equal to 1. I'm integrating with respect to y from 0 to z minus x, and then that has to be integrated with respect to x from 0 to z. Right? So when you do that, you get z square over 2, z square over 2. Right. So because that is this is z, this this length is z, this length is also z. So therefore, the area of this triangle is z times z divided by 2, z square over 2, and then the volume spanned by the surface is just you have to multiply by 1. So that's what you get here. Right? That's what you're supposed to get. And then, as I mentioned, in order to get when z in this interval greater than 1 but less than or equal to 2, the probability z equal to 1 minus the probability x plus y greater than z, right? So that area can be obtained again using this integration, right? In that case, if you are really doing the integration, you will be integrating for a fixed x. Uh, in that case, from uh, z minus uh, x to 1. First of all, you have to integrate with respect to y, and then uh, with respect to x, you have to integrate from, in this case, x will be changing from this point to this point. So that will be x equal to z minus 1 to 1. This one is z minus 1 here, right? Because uh, yeah, this is when y is equal to 1. When y is equal to 1, x is equal to z minus 1. Right? This point is z minus 1. This point is 1. Right. So you can get it as 1 minus this thing, and then this is the answer that you get at the end. This is the integration part, and then 1 minus that will be the uh, cumulative distribution function. Right. Therefore, you can write down the cumulative distribution function in two parts like this. Right? These are obvious parts of when z less than 0, the cumulative distribution function is 0. And if z simple z greater than 2, it has to be 1. Right? So those are always obvious parts. These are the two varying parts. Right? So if z is between 0 and 1, the cumulative distribution function is given by this expression. And if z is in this interval, then it's given by this expression. So this is the cumulative distribution function. So in order to get the density function, we have to differentiate this with respect to z. Then we get this expression here, right? So when you differentiate this, it becomes z, and then from the other one we get this. So that is how you apply the convolution formula to get the density function of the sum of two independent uniform 0, 1 random variables. So we have been asked to show that or illustrate this thing using simulation. So what I have done is actually I have several commands here. So first get x to be n numbers, uh, where n I'm going to consider 100,000 numbers. right? So here, that is the number of simulations actually I am going to consider, right? So I'm going to take some random numbers, again, the same number of random numbers, and then take, because these are independent, right? Numbers within X will be independently generated, Y will be, numbers within Y will be independently generated, X and Y are independent, so Z will be X plus Y, right? So now what I have to do is I have to uh, draw a histogram of this thing, right? Density histogram, right? So for that, I am considering uh, histogram of this Z breaks. I have actually considered the breaks to be, yeah, uh, 50. That means the number of breaks that we are considering, right? And then probability is equal to true. Otherwise, it will be drawing a frequency histogram, right? And X lim I have given to be 0, 2, because we know that uh, in this case Z, right? I'm looking at the possible values of Z, but of course it's called X lim because X axis represents Z. So Z values between 0 and 2, therefore. And Y lim, I have considered a reasonable limit. And then this will actually draw the histogram. And there are some other things that you want to add up, because you want to add the actual density function and also the estimated density using the kernel, right? So that's obtained using the density of Z, and then adding by lines of the density of Z, right? So I asked whether I want to, here the function asks whether you want to show the kernel density function, because it's obtained using something called kernel method, right? In addition to that, if I want, I can add the true density function that we derived right now. I am adding that also. So if show true is equal to true, then I can add the two, the fx function, right? Remember it had two parts. So I can draw those two lines using this command. So finally, I will have this picture here. So this black line and actually the kernel, they both are almost the same. Kernel density, that the estimated density. Uh, Dark line is the true density, and this part is the histogram. When you actually generate the data, right? It's actually the density function here is a uh, triangle, right? So it's a symmetric triangle, and also from histogram you can see that almost, because I have generated 100,000 numbers, right? 100,000 Z values. Right? So therefore, it's the histogram density histogram is going to be pretty close to the theoretical density function, right? Now there when I derive this thing, I used the density function as just one, right? One in the interval, density function of x is equal to one in the interval 0, 1, and also density function of y is equal to one in the interval 0, 1. And now there, I didn't have a function as such of x or y, but we can also do the same problem considering writing down the uniform density as a function of x. Right? There's a way to write down that using something called the indicator function. Right? So if I write down f of x of a uniform distribution, that is the density function of a uniform distribution, I can write down it as I01 as a subscript x. So this is an indicator function. This takes only two values. If this x is in this interval, then I01x will be equal to 1. If the x that we are considering here is outside this interval, then I01x will be equal to 0. Right? So that is the same as the uniform 0, 1 density. And then Fy will also be the same function, right? So here I'm going to consider this as my uh, density function of x and y, right? Now I want to find out the probability density function of z, right? So again, let us use the convolution formula, right? But now I'm going to write down, instead of 1, I'm going to write down the density function in terms of the indicator function, right? So therefore, if z will be equal to this expression, where now I can just replace this by this expression, and then fx x by this expression. Now, what is the product of these two functions? Right, this function will be equal to 1 only if z minus x is in this interval. This function will be equal to 1 only if x is in this interval. So this, therefore, the product will be equal to 1 if both of those things happen. That means z minus x has to be between 0 and 1, and also x has to be between 0 and. So that I can write down as the product of those two. That is equal to this expression here. So that, let me show you how that is obtained, right? So I01 is equal to 1 if x is in this interval. I0 z minus x is equal to 1 if z is minus x is in between 0 and 1. So this second condition I can write down again as inequality for x, like this, right? So that means this second condition happens if x is between z minus 1 and z. So I want now this and this both to happen, uh, because this product will be equal to 1 if those both of these conditions, the first one here and the last one here, are satisfied, right? So that means, therefore, the integrand is equal to 1, right? The integrand is this function here, that will be equal to 1 only if x is in this interval intersection this interval, right? So therefore, this integration now I can write down as this one. The other uh, the integration over the remaining part will be, of course, 0. So therefore, this thing can be written as, this thing becomes 1 now, right? On this interval, and then plus uh, integration of 0 over the whole other area. So therefore, this is what I am interested in now, right? This integration just of 1 in this subset. Now we consider again the possibilities of Z, as I saw earlier. He said we have to consider two cases because the areas have two different shapes. Therefore, we have to consider both cases separately, right? So if simple Z is between 0 and 1, then this intersection is simplified to 0 Z interval, right? 0, 1 interval. Notice Z is between 0 and 1. So in that case, 0, 1 interval intersection, this z minus 1 z becomes 0 z. I have graphically shown that. Let's take z to be a number between 0 and 1. This is the scale here. This is 0. This is z. Suppose this is 1, right? So z is now between 0 and 1. So in that case, 0, 1 interval is this interval, that is this interval, right? And then z minus 1, if z is somewhere here, z minus 1 will be somewhere here. So z minus 1 to z interval will be this interval, right? So the intersection of those two will be just this interval here, that is 0 to z interval. This is 0, this is z, right? So therefore, when if z is between 0 and 1, we'll have to just integrate here from 0 to z, right? 0 to z dx, right? And then, therefore, therefore, f z z is equal to z. If z is between 1 and 2, in that case, again, looking at the picture, we can see z is between 1 and 2, right? 2 is somewhere here, 1 is here. So if Z is here, Z minus 1 is going to be between 0 and 1, right? So then the intersection of 0, 1, 0, 1 is this one, Z minus 1, Z is this one. So therefore the intersection is now Z minus 1 to 1, this subject. So therefore in this case we have to integrate from this Z minus 1 to 1, and therefore the answer is 2 minus Z, right? So this is we obtain directly uh, applying to the convolution formula, right? So for all other Z values, the density will be 0. Therefore, I can write down the density of Z as this in two parts, which is the same as that we obtained earlier. So there I started with the cumulative distribution function and then differentiate the cumulative distribution function to get the density. But here, directly applying to the formula. Okay, let's look at another example. This is again from Demidon course book, example 3.14. A stick of unit length is broken at two random points. So the length of the stick is 1 unit, is broken at 2 points. Part A, find the CDF of the length of the shortest piece. Part B, check the theoretical CDF via simulations. Shortest piece and confirm your answer by simulations. So that's something I think some typing error. Then part C, find the length of the shortest piece and confirm your answer by simulation. So that is the same as there's something uh, repeated here by mistake because I copied the question from the book. I may have double pasted it somewhere. So anyway, the question is first of all to find out the CDF of the length of the shortest piece, and then get the same thing using simulations, right? So let x1 and x2 be the breakpoints, right? Right. So suppose the left end is point 0 and then right end is point 1, right, in a scale. Then there are 2 points where the stick is broken randomly. So in the scale, they will be x1 and x2, right? So that means from the left end to the first broken point, well, first broken point is denoted by x1, second broken point is denoted by x2. Right. So x1 can be anywhere in the interval 0, 1 uniformly distributed. X2 also can be anywhere in the interval 0, 1 uniformly distributed. So therefore, the joint distribution of x1 and x2, joint density function, can be written as this, right? Joint density function x1, x2 going to be 1 because x1 and x2 are independent. Joint density function will be the product of individual densities, therefore it's 1, but it is defined on the square given by x1 between 0 and 1, x2 between 0 and 1. Right? It's a unit square. Right. So what we are interested in the length of the shortest piece. So what can be the length of the shortest piece? For example, the length of the shortest piece can be x1 or it can be x2, right? For example, if the second broken point is close to the second end, so that may be the shortest piece. So in that case, length uh, no, x2 can also be left to the x1 also, because we are not considering here uh, the first point is x1 and second point is x2, right? Two values, right? So y can be therefore the minimum of these values, x1 or x2 or 1 minus x1 or 1 minus x2 or the absolute value difference between x1 and x2. So these are the possible lengths, and the shortest one will be the minimum of those. Possible lengths can be x1, x2, 1 minus x1, 1 minus x2, and then x1 minus x2. There are three pieces. There are three pieces. So, for example, x1, 1 minus x1, x1 minus x2. x2, 1 minus x2, x1 minus x2. Those are the lengths of three pieces. So therefore, the shortest piece, length of shortest piece will be the minimum of all those. Now, what are the possible values for y? Y is the minimum of these things. Therefore, y can take values only from 0 to 1 over 3. 1 over 3. That is the situation where uh, they are broken symmetrically. Right? Otherwise, y can be less than 1 over 3. Right? Y is the minimum. Right? So therefore, y is going to be in this interval. So let's take therefore a simple y in this interval and let's calculate the cumulative distribution function of y at that simple y. Here we cannot apply the uh, uh, convolution idea because this is not the max sum of two random variables that we are looking at. So here this is a different problem. But what we are looking at is how to find out uh, the density function of some function of x1 and x2. So by definition, this is equal to probability y less than or equal to simple y. And it will be easier to get write down this expression in terms of this x1, x2. If we write down like this, one is the same as 1 minus the probability y greater than simple y. Okay. Now remember, y is the minimum of these things. So minimum of several random variables. Each of these is a different random variable. So the minimum of several random variables greater than simple y, if and only if each of those random variables is greater than or greater than y. So therefore, this probability, I'm looking at the separately now. This probability is the same as probability x1 greater than y, x2 greater than y, 1 minus x1 greater than y, 1 minus x2 greater than y, and this absolute difference greater than y. Yeah. Because y less greater than y if and only if each of these random variables are greater than y. Each of is greater than y. Right? Now, this one, x1 greater than y and 1 minus x1 greater than y can be combined to write down this expression. That is, x1 is between y and 1 minus y. And similarly, x2 greater than y and 1 minus x2 greater than y can be written as x2 is between y and 1 minus y. And then finally, this thing. So these several expressions can now be simplified to reduce to these three expressions, the probability of happening these three events. Right, earlier I had 1, 2, 3, 4, 5, 6 events, but now it's the same as the intersection of three events. Right? So how do we get this probability? The probability regarding x1, x2, we have to integrate the joint density function with respect to x1 and x2 over a certain set A, where the set A is all simple x1, simple x2 points, satisfying simple x1 is between y and 1 minus y, simple x2 is between y and 1 minus y, and simple x1, simple x2 greater than y. Right? So we have to integrate over that area. Right. So here I have drawn that area as a diagram here, right? So that means I have to integrate. In this case, the density is actually just one, right? So integrate one over this area and this area. Right? So this is now this is the line x2 is this is x2 axis, this is x1 axis. This is the line x2 is equal to x1 plus y. This is the line x2 is equal to x1 minus y. Those two are showing actually this condition. X1 minus x2 greater than y. In order to look at that area, first of all, we have to look at x1 minus x2 is equal to y line, right? So because this absolute value, that means one line will be given by x1 minus x2 is equal to plus y. That will give you x2 is equal to x1 minus y. The other equation is x1 minus x2 is equal to negative y. That gives you x2 is equal to x1 plus y. So those are these two lines here. Right? And this area with the other two, right? X1 has to be between y and 1 minus y. X2 has to be between y and 1 minus y, right? So here x1, I have taken in this case y to be a particular value 0.2, but in general here we are interested in some y between 0 and 1 over 3. Simple y can be anything here, but in particular I have taken, because in order to draw the graph, I need a particular value. I have considered zero point 0.2, but in general here, this value will be y, this value will be 1 minus y. And this value will be again y, this value is 1 minus y. So x1 has to be between y and 1 minus y, x2 has to be between y and 1 minus y, and then x2 has to be less than this quantity and x2 has to be greater than, uh, yeah, in this case, this has to be satisfied x1 minus x2. So that is this area and this area with the intersection of the other previous two conditions. So therefore, what you want to do is integrate one actually uniform uh, joint density over this area and this area, right? So again, actually, we don't have to integrate in that case. The volume spanned over this triangle and this triangle will be equal to the area of this triangle plus area of this triangle. So in this case, we don't have to integrate, but I have just shown you how to integrate and get the answer. If you just find the area, you will get the same answers, right? So here, integrating, first of all, to get uh, the area, the volume over this thing, you have to integrate from here to here, and then x will be going from this y to 1 minus y, and then like that, right? Uh, x2 will be changing, if you consider, mm, yeah, x, if you, okay, yeah, I have here considered not the in the usual case. I would have integration. That's what I have been doing all the time, integrated with respect to x1 first and then x2 after that. No, actually, yeah, this is correct because I fix x1 at x1, right? So at x1, right? So this is the point where uh, x2 is equal to 1 minus y. And then this will be the point that uh, x2 is equal to x1 plus y, right? So that's why we are integrating from x1 plus y to 1 minus y with respect to x2, and then integrating with respect to x1 from y to 1 minus 2y, right? So this is y, and then 1 minus 2y. This is y. This is 1 minus y. This is 1 minus 2y, right? Because this is 1 minus y. When x2 is equal to 1 minus y, so this you get 1 minus y. So in that case, x1 is equal to 1 minus 2y. This y goes to this side, right? So when x2 is equal to 1 minus y, 1 minus y is equal to x1 plus y. Therefore, x1 is equal to 1 minus 2y. So we have to integrate. X1 will be changing from this value to this value here, right? So that's why you get this integration. The answer is this, right? So therefore, fyy is equal to 1 minus this value, right? Uh, and therefore, this answer here as the density function. So what I have done is actually integrated because the area, the volume spanned over this area plus this area will be twice the volume spanned by this area. So therefore, I have not integrated over this thing separately. I have taken twice of this. Right? That's why this 2 comes here. Right? This probability y greater than y. This is the integration coming when you integrate over this area, but its answer is going to be twice of that. That's why this area, right? Otherwise, I would have looked at the volume spanned over this area separately, but that's not necessary because this uh, you have a flat surface, and then you want the volume of that surface over this area plus this area, right? So that's twice of one area. Right? So this is the density function of y, where y is the length of the shortest piece, right? So now let us generate some data and see whether you get the same function as the density function. So here I'm generating data. I'm generating here 50,000 observations, 50,000 simulations actually I'm doing, right? So what I do is I take X to be two random numbers. Say, for example, those are the two break points between 0 and 1. So I take X1 to be the minimum of those, X2 to be the maximum of those two values. So then the length values can be X1, 1 minus X2, and then X2 minus X1. Length of the three parts, right? X1, 1 minus X2, and then X2 minus X1. So what I'm interested in the minimum, right? Minimum of L values. So therefore I take Y to be the minimum. Like that, I do it 50,000 times. So consider the minimum of these three places 50,000 times. Therefore, at the end, I have 50,000 possible values of Y, and then draw the histogram using this function here, and also draw the two right. Say for example here this is a linear function, no? Linear function in Y, right? So this will get 6 minus 18 times Y, right? So that is intercept is 6, slope is negative 18. I can draw that by giving this expression here, AB line. A is equal to 6 and B is equal to negative 18. B is the slope. So when I do that, you can see that this is the simulated data, density coming from the simulated data, and this is the theoretical density function. So you can see that they are pretty close. Right. So that is the time that I have for the second video. I will continue from there with this example and some more examples in the next part.